afternoon. I'm Sebastian and I did my senior thesis with Dr. Richard Walters. If you want to raise your hand as well. So we focused our research on the decomposition kinetics of polymers using thermal analysis. So some background. Polymers are long-chain molecules which are composed of repeating subunits called monomers. Monomers have simple structures which are often small hydrocarbon molecules. Linear thermoplastics were evaluated in this study. So here are like generic polymer structures. Our study focuses on all polymers that are shaped or like this for the sake of simplicity. When polymerized, these monomers form chains that are widely used because of they offer unique mechanical properties. Polymers are heavily used in the production of plastics, thin films, and adhesives, and various fibrous materials. So this is our instrument, the TGA, and our auto sampler and a feeding tray. This made for a lot of a greater capability of producing a lot of samples. Without that, we'd probably be stuck not running as many samples. I think we ran a total of 108 samples and lots of hours. Only twice did the instrument take a nap mid sampling. On the right here is our little sheet metal punch tool. Before cutting out the plastic, before using the punch tool, we used to cut the polymer samples with a razor blade and tweezers. But for the sake of consistency and replicability, we used the punch tool and documented the masses of each of the samples and and we just wrote them down so it'd be easier to reproduce later. This is a sample of one of the polymers, doesn't matter which, but they're all roughly this big and they all weighed about 5 to 8 milligrams. So starting off pretty strong with these graphs. These are mass loss curves that we plotted for specifically PMMA, which is polymethyl methacrylate, and alongside all the other non-charring plastics, and then PVC with the other charring plastics or polymers. They're all plotted at a rate of 10 degrees Celsius per minute for the sake of comparison. We'll get into the other rates soon. You can see their behaviors are much different than these. These polymers are called charring polymers because once they reach a certain temperature, they start to produce a kind of like a carbonaceous residue around themselves to where they will not continue to further degrade. So that's why they stop at the heating rates that we ran them at and not all the way at 0 because there's still residue or mass left over in the sample, from the sample. The non-charring species do not leave residue. So here are some of the other mass loss curves, but with all rates plotted. These are of the non-charring species. The legend is here. It's the same for each of the plots. The beta, or we defined heating rate is defined as beta. We have the yellow curve, or the blue curve at 2 degrees Celsius per minute, the orange curve at 5 degrees Celsius per minute, and the gray curve at 10, the yellow curve at 20 degrees Celsius per minute. If you take note of the right shift in the plots, the reason that this more rapid rate of heating, the reason for the shift is that there's a more rapid rate of heating, which forces decomposition to reach a higher temperature, which essentially causes the degradation reaction to take place more quickly. That's true amongst all 9 of the samples. The next slide will have the non-charring species. And these are the same plots just for the charring species. PI, polyimide, was used, or we only ran it from 5, 10, and 20 degrees Celsius per minute because using 2 degrees Celsius per minute would have been extremely time consuming. As you can see, we ran it up to 1100 degrees Celsius, so taking one measurement at 2 degrees Celsius would only add so much to the curve, so it wasn't very important to use 2 for that one. PVC behaves uniquely to the rest of the materials as it had a 2-step degradation reaction. Whereas a polymer like PMMA degrades in 1 step, PVC has to experience dehydroxychlorination before reaching the unzipping of the polymer backbone. So that's the result visibly if you were to want to visualize it. So this is the measured value. Basically, this is a breakdown of what we got from the TGA. This is just a mass loss curve, and this is an inverted first derivative curve of that same curve. This dotted line represents the peak temperature as well as the peak temperature on the mass loss scale. We use the STAR-E or the STAR-E software and extrapolated the first derivative mass loss curve and inverted it just to show that it comes like where the temperature value comes from each plot. So the figure on the left, I don't know if you guys can see this, d alpha dt with respect to time, and this is d alpha dt with respect to temperature. Both plots exhibit the same data, but the figure on the left is relative to the amount of time, and the temperature. There's a big peak, big spike in the temperature, just like we talked about on the other slide. This is because of the heating rate being amplified at a lower time. Since the rate of degree of conversion is amplified at higher values, we can determine from here we can determine temperature values outside the capability of a laboratory setting. We pick these rates because they're obtainable and they're easy to produce in a laboratory setting. You'll see in a future slide what I mean by the capabilities. So the basis of the mathematical computation came from the Arrhenius rate constant, which is for most of the people in this room have been taking Chem 4 or anything like it, are familiar with this equation. Once we obtain these values, modeling for the reaction mechanism was easily done by applying the differential form of the rate law of reaction, as well as the integrated form of the equation. And our target parameters were A, the frequency factor, and EA, which is D sub A, which is the activation energy. This is rough around the edges, as Rich said earlier. So this is the first mathematical method we applied was the Kissinger method. This is usually the go-to method in this type of analysis, and when you take the y-intercept, the y-intercept gives a frequency factor for each. These are all the materials plotted. So at the y-intercept, you have your frequency factor or your exponential factor. So in order to get, you use the slope from this equation to get the activation energy. You take the slope and multiply it by the gas constant and then divide it by 100, and you end up with the value, the two kinetic parameters that you were looking for from the start, or we were looking for from the start. So if you look at the R-square values for each, they're all pretty close to 1, meaning whatever we plotted the 4 rates on this line. If you wanted to, let's say, extend the line in either direction, you could get a good estimate on how the behavior of or you could get the values from a higher or lower heating rate, given that it fits the curve and that fits the line, and these lines are very close to 1. These are very small intentionally. These are the other onset temperatures, so these were the onset temperatures. These are the same graphs, but with different extrapolations done for different factors. So we had these two methods. We applied the Kissinger method, which took advantage of the peak temperature values, and then we attempted to take the onset temperature values and get a different set of kinetic parameters. Going back, this was the equation used for these. You guys saw this? And then this is the other equation. They're both the same, they do the same thing, but this is just easier to represent all of the graphs. So this table summarizes the results of what we got in those plots. So here we have the Kissinger peak, the peak REL, and the peak onset. REL stands for the Rich E. Lyon approach. He's sitting right here. We used the math to compare these kinetic values, and you can see the peak method using the REL approach and Kissinger method are almost the same. They only vary slightly in that temperature is squared in one of the denominators in the previous equation. And then the onset, the kinetic parameters obtained using the onset temperature have a different value. This gives insight that the difference in the first half of the reaction, there's a difference in the first half of the reaction than there is in the second, in the middle of the reaction, or the 50%. Here, these are just these numbers graphed, so you can compare them side by side. And yeah, the orange is the REL peak, and the gray is the Kissinger peak. Blue is REL onset. This chart is just a summary of the char yield exhibited by the charring species. All of them left behind some kind of amount. I just threw this in there because it was important to mention, because it was something that we did observe in the experiment. So some of the math models we used to fit the data were this REL function, the nth order function, which takes the value of 1 minus alpha and raises it to an nth power. The REL function is plotted in pink. The nth order value for this specific run at PMMA of b equal to 2 was a 1.77. And these typically follow a first order kinetic reaction. So this value is not too far off, but it's also working really nicely because PMMA behaves well. And then the black line is just PMMA, the raw data that we plotted. So when you integrate G of A, you get F of A, but it's inverted so we can see it in this form. The Gaussian fits the first derivative as the other two plots were sigmoidal. So that shape is just complementary to the first derivative form that we took from these equations. Typically, reactions take place from 0 to 100, and in this instance, we're losing mass from 100%. So the alpha, the frequency of the degree of conversion is 1 minus A rather than A minus 1 for alpha. So these figures represent all four models side by side, since the behavior of PMMA behaves similarly to that of expected first order reaction. PMMA was used to represent the figures which compare the behavior of normalized mass laws data, the nth order model, the first order model, and the Gaussian model, because it fit the behavior of the first order reaction best. There is more separation at these higher rates between the models because they just don't work as well as you would expect them to at, I mean, you wouldn't really expect them to, we had to figure that out, but they just don't work as well as they do at the lower rates. These are just a few we tried, and there are thousands of different methods to apply to this. So in summary, the thermal degradation of a series of polymers was measured using thermogravimetric analysis. Values for peak mass loss rate and onset temperature were obtained. The kinetic constants using 3 different methods were tabulated, and the models were evaluated with kinetic constants to recreate mass loss histories for comparison. The difference between these values of activation energy in A and alpha, or A, collision frequency, or collision factor, is indicative of the extent of change in the reaction mechanism. This varied between materials, as you guys saw in the plots. Some future applications may include collaboratively using this data with other thermal analytical techniques to produce fire models in programs such as Thermocam, which is a FAA produced system. I'd like to thank Dr. Walters for providing the opportunity to work alongside of him in the Fire Safety Science Laboratory at the FAA, Dr. Olson for coordinating with Stockton and the FAA and allowing this project to take place, as well as providing significant academic insight throughout my time here at Stockton, and Dr. Lyon for the insight on the material, as well as the thorough explanations of the mathematical theories derived and applied in this field.
Time for a couple questions.
No, don't see any.
Why is the FAA interested in understanding mass loss?
Well, if you consider this, the mass being lost in these thermal degradations is also considered fuel. So in order for something to burn, you have to have it in a gaseous form in order for oxygen to mix. And the plastics themselves can't just burn by themselves. They need to be gaseous. So airplanes are made of many different materials such as polymers. And in order to pick the best polymers to use to construct an aircraft, the ones that perform the best would probably be the ones that don't burn as much or lose as much mass. Mass is fuel. Oh, okay. Hey.
Were there any considerations on chain lengths for bulk thermal degradation characteristics?
No. Just weren't.